Hello everyone, I am Lu. I'm going to talk about a super-resolution model for mechanical LiDAR point clouds. This project was completed under the cooperation of BeiHang University and BeiHang Hangzhou Innovation Institute. The code is currently available on the GitHub platform. The super-resolution model for point clouds is to input a famous sparse point cloud and output a corresponding dense point cloud. The dense point cloud describes the surrounding environment in more detail than the sparse point cloud. Like the super-resolution task in images, dense point cloud correspond to high-resolution images, and the sparse point cloud correspond to low-resolution images. The sparseness or denseness of mechanical LiDAR mainly refers to the number of LiDAR laser beams. 16 and 32 laser beams LiDAR generate a sparse point cloud, while 64 and 128 generate dense point cloud. After being trained on the dataset, the super-resolution model embeds the potential prior features, such as the related characteristics of straight lines and planes, in the model weights. When in reference phrase, the model needs to run in real time. Since our model is a supervised neural network, we need datasets for training. There are almost no super-resolution datasets for point clouds, so we build datasets in the real world and the simulation platform. The real-world vehicle is a wire-controlled chassis equipped with a Robertson's 128 laser beams LiDAR. On the color simulation platform, we have established a 1-to-1 scale simulation vehicle based on the real-world vehicle. The LiDAR sensor simulation has also been implemented in the color platform. The simulation platform provides great help for the shortage of datasets for super-resolution tasks. Still, after using the data collected in the simulation platform, the model needs to be verified in the real world to realize the closed loop of modeling and algorithm verification. Our workflow is as follows. First, we need to build datasets for the LiDAR point cloud super-resolution task. Secondly, it is necessary to perform spherical projection transformation processing on the original point cloud to train the model more efficiently. Finally, use the processed data to train the established model. First of all, I want to talk about the establishment of datasets. We set the low-resolution LiDAR numbers of laser beams as 16 or 32, the high-resolution numbers as 64 or 128. Therefore, we collected 16 and 64 laser beams LiDAR data, 32 and 128 laser beams LiDAR on the simulation platform data. Totally 2 datasets. The left video shows the per point cloud of 16 laser beams LiDAR in the simulation platform, and the right shows the point cloud of 64 laser beams LiDAR. These 2 LiDARs are placed in the same position on the simulated vehicle. The corresponding LiDAR type in the real world are Auster 16 and Auster 64. As above, the left video is the point cloud of 32 laser beams LiDAR in the simulation platform, and the right is the point cloud of 128 laser beams LiDAR. The corresponding data type in the real world are Robertson's 32 and Robertson's 128. In the paper Simulation-Based LiDAR Super-Resolution for Ground Vehicles, Xiaoshan published a 16 to 64 LiDAR super-resolution datasets in the real world. So we only need to build a 32 to 128 datasets. But in the real world, It is impossible to put two different LiDARs in the same position, so we choose 32 laser beams from the Robinson's 128 LiDAR laser beams as the pseudo 32 laser beams LiDAR. The vertical scanning range of the real-world Robinson's 32 is the same as that of the Robinson's 128, so this method is very reasonable. After collecting the four datasets, 16 to 64 and 32 to 128 datasets in the simulation platform and the real world, we can proceed to the next step. The point cloud of LiDAR is a kind of non-Euclidean data that has disorder and variable number characteristics. Therefore, the point cloud needs to be Euclidean to use neural network models. The point cloud can be converted into voxel, graph, and other structures. But considering the real-time requirements for autonomous driving, it is a more reasonable way to convert the point cloud to the image. Therefore, we adopted a spherical projection mentioned in the RangeNet++ to project the point cloud into a range image. The non-ISO value pixel in the image represents a point in the point cloud. When the image resolution is large enough, it can be ensured that most of the points in the point cloud are retained, and this kind of projection is also reversible, and the image can be restored to a point cloud through a reverse operation. This can ensure that the super-resolution point cloud can finally be obtained. The temporal convolution characterizes our model T-UNet. The usual convolution is a spatial operation. When the input data is a time series, the network should also need to extract information in the time domain, such as trajectory of object. The temporal convolution is for operations in the time domain. Generally, RNN and LSTM are typical network models for processing time series data. They are all serially processing the data of each moment in the time series. It will cause great time complexity for processing image sequences. The temporal convolution uses shared weights in the same feature layer, which can process time series data in parallel and speed up the fusion of time domain information. The overall architecture of our model is a UNet, and the temporal convolution is mainly used for temporal information extraction in the encoder stage. Here is an example of a 16 to 64 super-resolution dataset. The details are as follows. The 16 continuous frame projection images of point cloud are the input data, and the image size is 16 times 1024. Each image frame is first passed through a two-chance convolutions of shared weights to increase the vertical resolution to 4 times the original. And now the image size is 64 times 1024. Then carry out 4 times temporal convolutions. The temporal convolution operation is as follows. Use concatenating operation in channel dimension. Two neighboring frames or images are fused, and then through two deleted convolutions, the time domain information is fully fused, and the size of the feature map is reduced by half. Replacing the polling layer with deleted convolution can effectively expand the reception field of convolution. After all 4 temporal convolutions, the feature map incorporating all frame information is obtained, and then, through a decoder similar to UNet, its feature map is connected with the same layer feature map in the encoder and transconvolved twice to obtain a larger size feature map. After several times of same operations, The feature map was finally restored to a high-resolution image size, 16:4 × 1024, and this image is the final output. Then we calculated the SSIM loss between the image and the ground truth image, and then we can carry out backpropagation. After being trained, the model was evaluated on the test datasets and visually displayed. This video shows the test result of the simulation datasets. The scene is an intersection. The left side is the input 16 laser beams LiDAR point cloud. The middle is the 64 laser beams LiDAR as the ground truth, and the right side is the super-resolution point cloud output by the model. It can be seen that the model performs better on flat objects such as walls and ground. These videos also show that test the result of the simulation datasets. The scene is the intersection. The left side is the input 32 laser beams LiDAR point cloud. The middle is the 128 laser beams LiDAR as the ground truth, and the right side is the super-resolution point cloud output by the model. It can be seen that the model performs better on the surface of buildings and trees. These videos also show that test the results of the simulation datasets. The scene is inside a tunnel. On the left side is the input 32 laser beams LiDAR point cloud. The middle is the 128 laser beams LiDAR as the ground truth, and the right side is the super-resolution point cloud output by the model. It can be seen that the overall performance of highly structured scenes, such as windows and tunnels, is better than that of orbitals. These videos show that they test the result of the real-world dataset, and the scene is the road segment. The left side is the input 16 laser beams LiDAR point cloud. The middle is the 64 laser beams LiDAR as the ground truth, and the right side is the super-resolution point cloud output by the model. It can be seen that the model performs better on the plane, which is consistent with the result on the simulation datasets. These videos also show the test result of the real-world datasets, and the scene is the road segment. The left side is the input 32 laser beams LiDAR point cloud. The middle is the 128 laser beams LiDAR as the ground truth, and the right side is the super-resolution point cloud output by the model. It can be seen that the model performs better on pavement, which is consistent with the result on the simulation dataset. In addition to virtual quantitative analysis, we also made quantitative comparisons with PSNR as the evaluation indicator. From the table above, we can see that our T-UNet model achieved a higher PSNR value compared to other three models. As for real-time performance, LSTM UNet can't achieve real-time effects at all, while our model can achieve near real-time on the current 4 datasets. We also used dilated convolution with a stride size of 2 instead of a polynomial in the experiment. From the results shown in the figure, whether PSNR or SSIM as an evaluation criterion, the dilated convolution has a better generalization effect than the polynomial. Finally, I make a conclusion. Dense point cloud from high-cost LiDAR support stable perception for autonomous vehicles and robots. However, the high cost also severely restricts related applications. To achieve better perception performance based on sparse low-end LiDAR, we designed a novel T-UNet model for point cloud super resolution. In the future, we will make several improvements. First, use transformer modeler to enhance accuracy. Secondly, compress the network by knowledge distillation to improve real-time performance. Last, further optimize the SSRM loss function to be more suitable for LiDAR point cloud super-resolution task. My presentation is over. Thanks for watching.